Okay, we're continuing with Chapter 11 in the statistics textbook. In this video, we're going to be going through the fourth section, which talks about looking at vertical strips. So what they're talking about is, on a scatter plot, you can choose like a small X interval, input interval, and you have like a vertical strip, right? So we want to take a closer look at some of the properties of data points within vertical strips and compare these properties between vertical strips. And this is going to be really interesting because what we're going to learn in this section is another way that we can analyze a scatter plot to see if it is football shaped. And we know that it's valuable to be able to say if a scatter diagram is football shaped, because then that means that it's applicable for the linear correlation coefficient in linear regression. So, okay, it says figure 8 repeats the scatter diagram for the heights of the 1,078 fathers and sons in Pearson's study. So this is, we saw this at the beginning of chapter 8. So here's that scatter plot they're talking about. You have the heights of fathers and the heights of sons, those fathers' sons. The families where the father is 64 inches tall to the nearest inch are plotted in the vertical strip on the left. A histogram for sons' heights in these families is shown at the bottom of the figure, solid line. The families with 72-inch fathers are plotted in the vertical strip on the right. A histogram for the heights of those sons is shown too, by the dashed line. So, okay, what they're saying is you've got this vertical strip here, which is at 64-inch input plus or minus a half an inch, and same idea here with 72 inches plus or minus a half an inch. And what they do is they take all the data points in this vertical strip, they take the Y values of these data points and make a histogram down here. And that's what the solid line histogram is. And then they do the same thing with these data points. That's the dashed line histogram. Okay, now they talk about how the dashed histogram is farther to the right than the solid one. On the average, the taller fathers do have taller sons. So yes, that makes sense. This is a positive, the correlation coefficient is positive here. And so in general, we expect that, like on average, the farther you are to the right down the independent variable axis, then the farther up you're going to be on the output axis. Like, even though you do have, here's a data point here, and then here's a data point here, you can find single data points that don't match this trend. On average, it's going to be, you're going up, right? On average, the taller the father, the taller his son's going to be. Now, but they then go on to note that it says, however, both histograms have similar shapes and just about the same amount of spread. So that's what's interesting here, is that if these two histograms, the solid and dashed, they're similar in shape and spread. One is just shifted relative to the other, okay? So it says that now when all the vertical strips in a scatter diagram show similar amounts of spread, the diagram is said to be homoscedastic, okay? The scatter diagram in figure 8 is homoscedastic. The range of sons' heights for a given father's height is greater in the middle of the picture, but that is only because there are more families in the middle of the picture, in the middle of things, than at the extreme. So yeah, what they're talking about there is, so when they're saying scatter, we're not just looking at the range, because if you think about just the range, well, then look in the middle here. You've got a point out here, you've got a point down here, right? The range is really high in the middle relative to at the ends, but that's just because there's more points in the middle. You have more opportunity for random chance, but the scatter in terms of standard deviation is going to be the same even in the middle, because you still have more points in the middle here pulling the standard deviation in. So what they're saying is the vertical strip, if you have a homoscedastic scatter diagram, then all of the vertical strips all the way through the input variables are going to have the same or similar amounts of scatter in terms of standard deviation. Okay? So now it says, yeah, the standard deviation of son's height for given father's height is pretty much the same from one end of the picture to the other. Exactly. Homo means same, scedastic means scatter, same scatter. Homoscedasticity is a terrible word, but statisticians insist on it. We prefer football-shaped. So yeah, there you go. Here's another test for this, a football-shaped scatter diagram, which again is really valuable for us to be able to test for this, because then we know it applies to the linear correlation coefficient and linear regression. Football shaped, that's like elliptical shaped, or even a perfect circle would be, that's still football shaped, but now the correlation coefficient is 0. But again, it's important to note, I've said this multiple times, just because the linear correlation coefficient is 0 doesn't mean, oh, it's not applicable for the linear correlation coefficient. No, it could be perfectly applicable. If it's a perfect circle, then it's just the data is just randomly scattered in a circle. That means that the linear correlation coefficient is telling you there is no correlation here, right? But it could be the circumstance that you have a linear correlation coefficient equal to 0, and that means that no, it just doesn't apply to linear regression, or it doesn't follow a linear pattern. But if it's football shaped, if it's homoscedastic, then the linear correlation coefficient is telling you, no, there is no correlation here. Okay, so when the scatter diagram is football shaped, the prediction errors are similar all along the regression line. So here's another property of homoscedastic data. The prediction errors are similar all along the regression line. In Figure 8, the regression line for predicting sons' height from father's height had an RMS error of 2.3 inches. So we know we can calculate that with the square root of 1 minus r squared times the standard deviation in the output variable. If the father is 64 inches tall, the prediction for the son's height is 67 inches, and this is likely to be off by 2.3 inches or so. If the father is 72 inches tall, the prediction for the son's height is 71 inches, and this is likely to be off by the same amount, 2.3 inches or so. So what they're saying is that if you have a football-shaped scatter diagram, homoscedastic, you make a regression line, then the prediction errors are the same no matter where you are on that regression line. Remember what RMS, what it means is that it's the general uncertainty of a prediction. Look, this is my prediction for I'm given an input. Here's my prediction for the output, and I'm going to be off by, I'm uncertain to within this amount. That's the RMS error. And they're saying that with homoscedastic data, that's the error no matter where you are on the line, on the regression line. That's a property of homoscedastic data. Now, if we look here, it says, by comparison, Figure 9 shows the heteroscedastic scatter diagram of income against education. Hetero means different. As education goes up, average income goes up, and so does the spread in income. Okay, so let's come here. What they're saying is that, so this is not football shaped, right? This is not football shaped. And so, maybe we want to model this with some sort of exponential regression. But what they're saying is what you can see, they start off by just saying that it's like you can still calculate the linear correlation coefficient and do linear regression on any set of data you want. It doesn't matter, right? It might not be applicable for the linear correlation coefficient or linear regression, but you can still do it. And so, but like the linear correlation coefficient would tell us that, it would tell us in this case that it probably would sense that the positive trend. Okay, but what they're pointing out is that as the educational level goes up, so does the spread in income, right? So if we come back here, when the scatter diagram is heteroscedastic, the regression method is off by different amounts in different parts of the scatter diagram. In Figure 9, the RMS error of the regression line is about $19,000. However, it is quite a bit harder to predict the incomes of the highly educated people. With 8 years of schooling, the prediction errors are something like $6,000. At 12 years, the errors go up to $15,000 or so. At 16 years, the errors go up to $27,000 or so. In this case, the RMS error of the regression line gives a sort of average error across the different X values. So yeah, the heteroscedasticity is just saying that it's harder to predict income level if the higher the education level of the person. So that's why if you have a lower level of schooling, you can see the errors are lower. The errors get bigger and bigger as you get to higher and higher levels of schooling. So now, what does the RMS error mean in this sense? Because again, we can still calculate a single RMS error value. Well, that's just an average of like all of these. So you would say if you were here, if you were doing a prediction for an educational level in this range, then you would take the RMS error and scale it down a little bit, maybe by 20% or something. or no, you would scale it. No, you'd scale it up a little bit. Instead of using, okay, hold on. You would get an RMS error probably somewhere in the middle here. Okay, so yeah, if you're in this region, then you'd want to take that RMS error and scale it down a little bit. If you're in this region, you want to take that RMS error and scale it up a little bit. But on average, if you did have the exact RMS error values all along the line, on average they're going to equal the RMS, the square root of 1 minus r squared to the or times the standard deviation in the output direction. But again, even though you could calculate RMS error and do a linear regression on any set of data you want, if it's heteroscedastic, we have to ask the question, well, maybe any heteroscedastic data isn't appropriate for the linear correlation coefficient or linear regression, because we can just think about here, maybe what about an exponential curve fit, right? Okay, so suppose that a scatter diagram is football shaped. Take the points in a narrow vertical strip. They will be off the regression line up or down by amounts similar in size to the RMS error. If the diagram is heteroscedastic, the RMS error should not be used for individual strips. Okay, so yeah, you can use, if it's football shaped homoscedastic, you can use the RMS error, the linear RMS error for, to state your prediction errors in all circumstances. If it's heteroscedastic, then you're going to need to use some other method. I mean, it's not like maybe you couldn't use the RMS error, but maybe you'll have to adjust it depending on the region you're in. But for the moment, we'll just say you can't use the RMS error. You can't state the RMS error if it's heteroscedastic. At the moment, we'll just say that. Okay, now let's go through these exercises. In 1937, the Stanford-Binet IQ test was re-standardized with two forms, L and M. A large number of subjects took both tests. The results can be summarized as follows. So we've got the same average for both tests, the same standard deviation, and a correlation coefficient of 0.8. All right, true or false and explain. The regression line for predicting the score on form M from the score on form L has an RMS error of about 9 points. So here, all we need to do is just use the formula, 1 minus r squared, the square root of that, times the standard deviation. This is RMS. The standard deviation with respect to the output variable, well, they're the same in both cases, but the output variable would be, if they were different, we would use, for predicting the score on form M from L, so we would use this. Now, you might be saying, well, wait a minute, don't we have to check to see if it's homoscedastic? No. You can calculate the linear RMS error, even if it's the worst it could possibly be in terms of for linearity. You can still calculate the RMS error, right? So is it 9 points? 1 minus 0.8 squared times 15, 9. So yes, that's correct. Okay, now suppose the scatter diagram looks like number 1 here below. If someone scores 130 on form L, the regression method predicts 124 for the score on form M. They're telling us that. True or false and explain. This prediction is likely to be off by 9 points or so. Well, now we need to know if it's homoscedastic or football shaped, because now we have a specific case. They're saying, look, okay, you have the RMS error, and now we're doing a linear regression prediction. Okay, can you say that that prediction is off by about 9 points, the RMS error? Well, okay, in order for us to say this, it needs to be football shaped. Otherwise, we can't. We need more information, right? So 1 is football shaped, so 9 points is the RMS error, so true. Okay, repeat if the scatter diagram looks like number 2. So yeah, this is heteroscedastic. So no, we can't make this statement. False. Because if we're in this region here, then the actual RMS error is lower than than 9 points. If we're here, it's higher than 9 points. If we're kind of in the middle, then maybe if they told us we're in the middle, then maybe we could say that it's off by 9 points. That still probably wouldn't be enough information, but maybe you could say that it's close to 9 points, right in the middle here, because it's going to be on. Why I'm saying that, because it is, if you took like the average of of all of these values here. Well, even that's not. It's not the. It doesn't go to the outskirts of the cloud. It's more of the standard deviation. So right. So in reality, it would be you would have a linear regression line would be going through like something like that. I guess, or probably that's the SD line. So it would probably be more like this. And you'd have to kind of say, well, at each of these, what's the standard deviation, and take the average of those. And so, yeah, not enough information. Okay, the data in Figure 8 can be summarized as follows. Let me bring in Figure 8. Okay, there's the average height of fathers, sons. Once again, the same standard deviation for both the input and output in this case. R is about 0.5. So, okay, find the RMS error of the regression line for predicting son's height from father's height. So again, we can just, this is easy. It doesn't matter if it's football shaped or not, even though it is in this case. So we've got 1 minus 0.5 squared times 2.7. The output would be the predicting son's height from father's height, but it's the same standard deviation in this case regardless. So 1 minus 0.5 squared times, so 2.34. Okay, if a father is 72 inches tall, predict his son's height. So, okay, this is just regression, right? So what we do is we say the father is 4 inches above average. How many standard deviations is that? Okay, so now we usually would have to kind of apply this to, we're 1.48 standard deviations above average in the X. So now we need to apply this to the other standard deviation. But since they're the same, we can just say, okay, multiply this by the correlation coefficient. And that's how many standard deviations we need to go up in the Y. And so this is, so now we multiply this by 2.7. And there you go. So it's 2 inches above average in the output. That's 71-inch sons. So this prediction is likely to be off by, this is football shaped, so 2.34 inches. Okay, repeat parts B and C if the father is 66 inches tall. So the father is 2 inches below average. That's how many standard deviations? That's that many standard deviations. Okay, now we want to multiply this by the correlation coefficient, right? This is all just what we learned how to do linear regression. And there you go. So it's that many standard deviations. We need to go down. So multiply that by 2.7, -1. So average height of the, so we're 1 below average for the height of the sun. So that's 68 inches. And we're off by 2.34 inches. It's football shaped. It's homoscedastic. Okay, now we've got next for part 3, we're going to be looking at, or question 3, we're looking at figure 9. Okay, there's figure 9. So, okay, we've got the data is, here's the average education, average income. Here's the standard deviations. Now there are different standard deviations. So this will be, we'll just get some more practice with regression, better practice this way. R is about 0.37. So, okay, find the RMS error of the regression line for predicting income from education. So it doesn't matter that it's heteroscedastic. It's just 1 minus the correlation coefficient squared times the standard deviation of the output variable. That's the income level, so $20,000. Let me rewrite this. So 18,581 is the RMS. So, okay, now predict the income of a woman with 16 years of education. So linear regression is linear regression. It doesn't matter if it's not football shaped. It's still the same process. So you're just going to do, let's see. We've got, if a woman has 16 years of education, she's 3 years above average. That's how many standard deviations? That many standard deviations. Okay, so now $20,000 this many standard deviations of $20,000 is this, right? But we want to multiply that by 0.37. We don't want to go a full a one-to-one standard deviation with respect to both variables. Then we'd be on the SD line. We'd be on the SD line. If we went this many dollars above average income, we'd be on the SD line. We want to follow the correlation coefficient. So it's this many dollars above average, like that. So 24,529. Okay, this prediction is likely to be off by how many dollars? We don't know. It's heteroscedastic. But I mean, we could, where are we? We're at 13, we're at 16, so it's going to be, we know it's going to be higher. We can see visually it's going to be higher than this, but we can't say. Okay, repeat parts B and C for a woman with 8 years of education, so that's, let's see, 5 years below average. How many standard deviations is that? Okay, so apply that to the $20,000, and now, well, times 0.337, and now add this to 18,000. 7,118. Okay. The figure below is a scatter diagram for the ages of husbands and wives in Indiana. Data are from the March 2005 Current Population Survey. The vertical strip represents the families where the what is between what and what years of age. So, okay, this vertical strip here is it's mapping out or focusing in on an age of husbands between age 20 and 30, right? Okay, so now continuing with this same problem here, fill in the blanks using these options. The average age for all the husbands is about what, and the standard deviation is about what? So for all the husbands, so okay, where's the point of averages? About around 50. Is 50 an option? Yes. Okay, what about the standard deviation? So something like that, maybe. What is that? Oh, for the husband. Sorry. So that would be, we're going in this direction. Something like that. So 15-ish. Could it be 25, 50, 60? That would be coming out to here. That's too much. It's got to be 15. Okay, now the average age for all the wives is about what, and the standard deviation is about what? So, okay, where it's like 50, and it's 50, and looks like also 15 as well. So, okay. The correlation between the ages of all the husbands and wives is about, so the entire correlation, this looks like a really good correlation, so it's, what are the options? It's not 1. 0.95, yeah, maybe, but it could be like 0.85, 0.8, maybe 0.75, probably no lower than that. Well, there's no option. It goes from 0.95 to 0.5. That's too low, so 0.95. Among families plotted in the vertical strip, the average age for the wives is about what, and the standard deviation is about what. So, okay, so in here we've got, there's the average at about, what's that? 30, 25-ish. So 25. The standard deviation is about what? 10 or 5? Not 15, so 5. Not 1. 1's too low. Among families plotted in the vertical strip, the correlation between the ages of the husbands and wives is about what? Okay, well, we know that it's a similar degree of scattering about a line here in this region as it is in the entire region. But remember, that doesn't mean that it's the same. The correlation coefficient is the same. That means it's actually going to be higher than, or no, it would be lower than what it was for the entire data set, because you have, if for all things being the same, if you have a bigger range, then you have a better correlation coefficient. So this is going to be lower than 0.95 for sure. Now, how much lower? I mean, okay, I don't know if I'd say 0.5, but I mean, that's the next option. It's not 0.95 for sure. Even though it's the same degree of scattering, but the range is smaller, right? So it's the next best option. This is too low. The next best option is 0.5. Okay. Now, same problem, but different questions. The standard deviation is computed for the ages of all the wives and the wives whose husbands are 20 to 30 years old. Which standard deviation is bigger, or are the standard deviations about the same? Well, we just did this. The standard deviation for the entire data set is bigger. That makes sense, right? We just saw that. They're talking about the wives. It was we got about 5 here, and then for the entire data set was about 15. Now you might look at that and say, well, wait a minute, I thought it was homoscedastic. The standard deviations are all the same. Yeah, that's between the vertical strips. We expect if we did another vertical strip here, and another vertical strip here, and another vertical strip here, and here, we expect the standard deviations for all of these vertical strips to be around 5. But it's different when we're looking at the entire data set. Okay, so now the standard deviation is computed for the ages of all the wives and the wives whose husbands were born in March. Which standard deviation is bigger, or are the standard deviations about the same? So, well, this is going to be, assuming we have enough data points, it's going to be the same, because the whole idea here, when it comes to the husbands born in March, well, we're not mapping off or boxing in some specific region of the data points. A husband with any age could be born in March. Right? That's not, we're not, if we come back here, if we have husbands born in March, that doesn't mean that, okay, we're going to be in this region. No, it's going to be, as long as there's enough data points, you're going to get they're just going to be randomly scattered around the same shape here. Now, yeah, if there's only like 3 people born in March and you just have like 3 data points, well, okay, that could change things, but that's not what they're suggesting. They're just trying to indicate that, look, if this was a huge data set and you just took off you singled out the men born in March, well, you could get the same shape. It's just random. And so that's going to be the same standard deviation. In one study of identical male twins, the average height was found to be above 68 inches with a standard deviation of about 3 inches. The correlation between the heights of the twins was about 0.95, and the scatter diagram was football-shaped. Okay, so we have identical male twins. Average height was found to be about 68 inches with a standard deviation of about 3 inches. So, okay, I guess that's going to be the same average height and standard deviation for both the identical twins. I guess that makes sense. And we would expect this scatter plot to be like on a 45-degree line, tightly clustered. High correlation coefficient, right? In other words, here's twin 1, here's twin 2. We expect the heights of twin 1 and twin 2 to be about the same. Like if we have twin 1 that's this height, then we expect twin 2 to be about that same height, right? Now, on average, they're about 68 inches. Okay, so you have to guess the height of one of the twins without any further information. What method would you use? Okay, well, without any further information, we just use the average, right? We use that baseline method to where it's like, okay, we don't have a regression line. We don't have an input, so the regression line becomes the horizontal line that goes through the average. And then the RMS error is the standard deviation in the y direction, right? Because all of the deviations from the average, you take the RMS of that's the RMS error. Well, that's the standard deviation in the y direction. So we would just say that, we would guess that, okay, it's 68 inches, with the RMS error being the standard deviation in the output direction. That's it. That's all we can do. We can't use the regression line. They're not giving us what the input is. Right, we talked about that. That's when this becomes the regression line, and the RMS is the standard deviation. Because again, what is the RMS? It's the deviations of all the data points from the regression line, take the RMS of those deviations. Well, in this case, the deviations of all these points from the regression line, that's the deviations from the average. Well, that's what the standard deviation is, right? Okay, so now, but one twin of the pair is standing in front of you. You have to guess the height of the other twin. What method would you use? Okay, so what they're saying is that you can see that the twin is 6 feet 6 inches tall. So yeah, well, here you just use regression, right? They're telling us it's football shaped. So we can actually use linear regression. We know it's going to be applicable, and we can use the RMS. So we've got, let's see, it's going to be, you've got a height of, 6 feet 6 inches is 78 inches. So that's 10 inches above average. That's how many standard deviations. Okay, but now we need to take this and multiply by the correlation coefficient. Now we're that many standard deviations on the output, so we multiply this by 3 again. And now add this to 68. So 77.5 inches, 6 feet, 5.5 inches. Okay, but now what's the RMS error for what we just calculated? That's going to be 3 inches. It's football shaped.